Right, I think we should probably get started because, as some of you might be able to guess, this might be a little bit of a long presentation. Hello and welcome. I'm Andrew Cooper. I work for Citrix on the hypervisor team. I also have a number of roles and responsibilities in the upstream community. Today I'm going to be talking about x86 stack switching and a number of the problems that come with this. And also be covering some of the proposed solutions from Intel and AMD. First things first, some theory about stacks. Hopefully everyone watching this presentation will know that stack is supposed to be a last in, first out data structure, and we use this to get correct nesting of function calls primarily. A couple of things you should not do with the stack. You shouldn't accidentally edit the return address in particular. That leads to a lot of exploits. And hopefully it goes without saying that user space should not be able to write to the in-use kernel stack. The other thing that must not happen is you must not reuse an in-use stack, otherwise both of the users will end up malfunctioning, again, mostly because the return address gets corrupted. And with that in mind, to discuss x86, we have to go back in time a little bit to, I believe, 1982, when the 286 processor was introduced and introduced protected mode into the architecture. In the x86 architecture, this comes with 4 rings of protection, it has 4 stacks. If an interrupt or an exception occurs, then a stack switch might need to occur. If you take it at the same privilege, you use the same stack. If you need to change to a higher privilege to handle it, you switch stacks. If you need to switch stacks within the same privilege, then you can use a task switch for that purpose. This is the x86 hardware task switching mechanism. And much maligned as it is, it did come with one fantastic feature, which was the busy bits in the GDT, which would prevent re-entrant use of a task. The 386, a couple of years later, obviously a lot of things changed between 16 and 32-bit architecture, but the fundamentals of this area didn't change too much. Already at this point, there was a bit of problems, mostly to do with error code handling. Because the IDT is overloaded in terms of how exceptions and interrupts and external interrupts get generated, whether you have an error code or not is complicated, and in particular there are ways to invoke, for example, the logic that should be the general protection fault handler without an error code. Also, the legacy PIT defaults to this range because it dates from a period where exceptions weren't specified this high in the numbering scheme. So overall, trying to look at this, on the left-hand side, you have the task state segment, and inside it has references to the ring 0 through ring 2 stack. It doesn't need a reference to the ring 3 stack because that you're never in a position where you need to find the ring 3 stack to asynchronously move execution to. A common setup in a 32-bit operating system is to program the double fault handler as a task switch. In particular, this lets you catch stack overflows, and in this case, it will use the hardware task switching mechanism to switch to a new double fault stack, which is usually there to provide just enough ability to dump a backtrace and then crash. Already in the architecture at this point was a curious thing called interrupt shadows. And these come from 2 cases where atomicity was really required but couldn't be expressed easily. All pointers, all memory addresses in x86 are actually formed of 2 registers. You have the segment for it and the pointer. So for the stack in particular, it's the stack segment and the stack pointer. But to update which stack you're on, you need to change both of these. And those are 2 separate instructions. As a consequence, a move to SS has a side effect of blocking interrupts and traps for one instruction. The idea being that you could execute a move to SS, then a move to the stack pointer, to atomically switch which stack you're on, and in particular, so you cannot take an external interrupt whilst you're halfway through this and you have junk instead of a working stack. The 386 processor introduced another instruction called load stack segment that could update both of them atomically, but this had been a problem in the 16-bit architecture as well. A separate issue is to do with trying to go to sleep with interrupts enabled. Enabling interrupts is one instruction, the STI instruction for set the interrupt flag, and halt is a second instruction. And the problem here is if, for example, you're waiting for a timer interrupt and the timer interrupt hits between the two instructions, you can end up servicing the timer interrupt and then going to sleep with no further interrupt to wake you up. So again, in this case, an STI instruction has a side effect of deferring the recognition of external interrupts until one instruction later. In both of these cases, it doesn't affect things like faults to do with fetching and decoding the instruction, so page faults still get in the way. This is important because, particularly in Windows, the STI halt is used all over the place as part of message passing between logical levels in the kernel. Fast forward a few years from the 386, and it had been decided that the way of doing system calls was a little bit slow, so the traditional way is int80, and the reason it's slow is because microcode has to parse the IDT, the GDT, and the task state segment if you're changing privilege. Even by that point, common architectures were predominantly using flat segmentation and only two privileges because it was similar to other CPU architectures existing at the day. So Intel in the Pentium 2 introduced sysenter and sysexit, and AMD with the Case 6 introduced syscall and sysret. Both of these speed things up by not referencing the GDT or the IDT at all and loading with fixed attributes, but both of them come with rather crippling bugs. Sysenter decides that you didn't need to know the instruction pointer in user space, or the stack pointer, but syscall doesn't actually switch the stack, which leads to a problem called the syscall gap. In this case, user space executes the syscall instruction, we switch into supervisor privilege, and the kernel is responsible for switching the stacks. A consequence of this is that the stack pointer is entirely user controlled at this point. Now, commonly it will point at the user stack, but you can get some rather more cunning user space which might point it at a kernel address rather than a user address. As a result, you must not take any interrupt or exception at all until the stack has been switched, because in one case, user space can clobber its choice of area in kernel memory, and in the other case, the kernel interrupt handler starts running on a stack which user space can write to. Various interrupts and exceptions behave asynchronously. Debug exception, technically not, but because of the moveSS delayed shadow, it can be deferred and appear on the wrong instruction boundary. So in particular, you can cause it to be delivered after syscall has completed and before you have had a chance to switch stack correctly. The non-maskable interrupt and machine check exceptions both behave logically like external interrupts, and you can't block them. VE and VC are used predominantly in encrypted VMs these days, and they're notifications that the guest kernel needs to do something. HV, again, is used with AMD's encrypted virtual machines. It's a notification explicitly from the hypervisor to the guest kernel that an interrupt is pending, and therefore it has NMI-like behavior. There's also security exception, which dates back quite a while. That is to do with root of trust bring up on AMD systems. NMIs are by far the most problematic of the lot here because they are the most common to find. They are used frequently for performance profiling and watchdogs and other things like that. They are non-maskable. The name is hopefully a bit of a giveaway, But even in the early architecture, it was discovered that trying to run these reentrantly was not a clever idea. So inside the CPU, there is an NMI latch. It gets set when the NMI handler is invoked, and it gets cleared on the next IRET instruction. This means that if you have several NMIs appear in quick succession, the second one waits until the handler is complete for the first one. And that would be great if it worked like that. The problem is that inside an NMI handler, you could, for example, take a nested exception. So read MSR safe, write MSR safe, something like that. Also, page fault is very common, particularly if you're using perf under Linux. Then the perf event subsystem will, for example, go and read the user stack to try and build call chains for you. So you can, in reality, get legitimate situations for nested exceptions, and the problem is that the first IRET instruction unblocks NMIs, not the one that was logically associated with the NMI handler. Intel CPUs have a further bizarre piece of behavior here, which is the fact that the NMIs get unblocked even if the IRET instruction faults. This is atypical to do with faulting behavior in the architecture, and it's problematic because user space can force an IRET instruction to fault if, for example, it has access to the modify LDT system call. The reality is that trying to make your NMI handler safe to this is actually quite difficult. You can go and look at and see how the Linux kernel does it, but it is not easy. Later still, in the mid-2000s, the 64-bit spec came along. Syscall is now mandatory, so all your stack problems are mandatory, and task switches are persona non grata. They are replaced with a mechanism called interrupt stack tables. Unlike task switches, interrupt stack tables have no reentrancy protection, and they function by resetting the stack pointer to a fixed value, which means that if you actually re-enter an interrupt stack table, you reset to the base of the current stack, and you end up using you end up running both handlers on the same stack, and they corrupt each other. Also, there are only 7 IST vectors, and those of you who were counting carefully 2 slides ago would notice that I listed 7 vectors needing various protections in the syscall gap. The other thing introduced by the AMD 64 spec was the reuse of GS as 2 different pointers, one for user space and one for kernel space. And there's a swap GS instruction for doing this, but it means that the user and the kernel bases are not swapped atomically. If you get this wrong, you end up with a per CPU memory access using the user pointer rather than the kernel pointer, and everything goes sad as a result. Normal interrupt handlers must conditionally swap GS based on whether they're interrupting user space or kernel space. And the async exception handlers, which we looked through before, need to cope with that, as well as being able to cope with the areas of the kernel where you happen to still be using the user pointers because you hadn't got around to switching them at that point. This is what the result looks like. It's quite similar to the 32-bit days. The task state segment still exists, but it basically only has these pointers in it. The new thing are the interrupt stack table pointers. There are up to 7. You can point to them, and for all intents and purposes, they are logically ring 0 stacks. Fast forward to a year ago, and the set specification came into existence. So this is control flow enforcement, and in particular, it's looking to try and protect against ROP attacks. sysenter managed to introduce the same bug that syscall had. Sysenter will switch the regular stack, but doesn't switch the shadow stack. Which creates exactly the same problems as syscall has, even under set, which means that if you want to use set, you can't even disable syscalls to get your security back. Set did try to fix the reentrancy problem in shadow stacks. There's now a busy bit on the supervisor stacks. to detect and prevent cases which would corrupt an in-use stack. The problem is that all the work to fix the NMI handler to not explode doesn't remotely look like a sensible use of a stack, and it is an open question as to whether that can even be made to work in combination with set. A couple of other minor irritations, because of course if we're going through these we might as well fix all of them. For the page fault and debug exceptions, there's extra status information in CR2 and DR6. You need to read those and preserve them before taking a nested page fault or a nested debug exception. And context switching between two pieces of user space involves corrupting the kernel CPU pointer for a minimum of one instruction, because you've got to reload GS, and that clobbers the kernel base pointer. Everything else there is a little bit more minor, but in particular causes some of the irritations. For example, espfix. Now, when this was pointed out, various of the vendors said, "Oh, yeah, that's kind of bad, isn't it?" In reality, whilst a lot of these corner cases sound rare, they, in the size of a data center, you've got problems happening with this multiple times a day. So it might be rare for an individual to encounter this, but across the industry as a whole, it's quite bad. AMD have proposed a spec called the supervisor entry extensions. Intel have proposed a spec called the fast return and event delivery, or flexible. We're not quite sure. It changed its name. We'll get back to that in a moment. Both of them are currently in draft, and both of them are currently soliciting technical feedback, which is excellent timing for this. The details I'm about to cover are accurate as of today. If you are listening back on a recording in the future, they are unlikely to be accurate at that point. So, the AMD SEE draft 0.5, the main intent here was to remove the use of interrupt stack tables. Of course, we want it for double fault because we need to re-establish a good stack there, but the majority of the problem in 64-bit operating systems is the behavior of IST. So we get a new register to hold the stack pointer and a new control bit to change the behavior on entry and exit. So syscall now switches the full stack, writes a full IRET frame, which it didn't previously, automatically swaps GS, and if shadow stacks are enabled, automatically switches the shadow stack as well. There's already a shadow stack pointer, it just wasn't done automatically previously. Something a little bit on the side is a mechanism to change how the busy bit handling works for shadow stacks. AMD have decided that the overhead of it is actually quite large, and there might be better ways of trying to fix the reentrancy problem. The other bit you get is partial FS and GS loading. This is specifically to load the bits that we need for a context switch without clobbering the kernel base pointer, which is typically in use for the kernel per CPU data. Another bit in the draft is the reentrancy protection. This revolves around a new MSR called the exception in progress. So a new exception becomes marked in the MSR, and an attempt to re-enter a protected vector results in a double fault, i.e. you will get a clean double fault rather than accidentally clobbering state on, for example, CR2 and DR6. There's extra metadata saved in the IRET frame. You get the vector number and the exception valid bit. In particular, exception valid lets you now deal with the fact that you know what is logically the end of the NMI handler, because the end of the NMI handler is the IRET that sees exception valid and vector 2. So this lets exceptions nest correctly inside an NMI handler without unblocking the NMI shadow. One fantastic piece of this spec is the ability to actually mask and unmask NMIs by using the NMI bit in the exception in progress MSR, which avoids us having to deal with some of the silly things we we deal with to block nmis in certain cases. Because it turns out you can mask them if you send an nmi to yourself to manually set the latch. The other bit of metadata is the interrupt shadow, and that's specifically to allow establishing the STI block. That is basically so you can handle page faults. In the example we saw earlier with trying to enable interrupts and go to sleep. So that's a quick look at the AMD version. The Intel version is called Fred. This is a rather larger change to the architecture. It sits there and tries to remove the IDT and the TSS from all event handling. For the same reason that syscall and sysenter were introduced, you can speed things up a lot by not having to read a whole load of tables in memory. At the point that IDT and TSS were taken out, I actually requested one extra feature and they said yes. So call gates are also removed from the architecture. You can't use call gates because they have binary differences between Intel and AMD, so no one uses them. And the moment you remove call gates from the architecture, then there are now no longer any entry points into the kernel rooted in memory. So this removes an entire class of attack and means that that an attacker has no reason to go and try and find a writable pointer to the GDT. They're going to have to find some more interesting way of escalating their privilege as part of an attack. The Fred spec introduces a new CR4 bit and a new concept called the current stack level, which is there to replace the previous interrupt stack tables. There are 4 CSLs, 0 to 3, and there's a running total of the current stack level and which stack the new event would like to use. You always run on the max of these 2, and anytime CSL changes, you switch stacks. There are a bunch more MSRs now to deal with this information. And again, as with the AMD side, Intel proposed a way of changing how the shadow stack busy bits work, again, to reduce the overhead. An interesting property of Fred that was clearly requested by one vendor was trying to add support for red zones in the kernel. This is important for some forms of optimization, and it means that if you're doing microkernel development now with kernel code, you don't need to supply no red zone to make your code work correctly. This is an attempt to represent what it looks like, and hopefully you will agree it is far more simple than the previous diagrams. There's the user space stack and 4 stack pointers. There's a parallel set for the shadow stack pointers, but that's that. I haven't included shadow stacks in any of these diagrams. There's a substantial extension to the IREC frame on the stack. Again, you get the vector number now. You also get type. So this is as per the VT spec. Those of you familiar with hypervisors will instantly recognize those types. The error code is presented unconditionally, or 0 if it's not relevant. Various extra status registers, so CR2, DR6, or XFD, are presented in the stack frame, or 0 if not relevant. And there's also extra metadata in there for a similar kind of reason as before. There are 2 new instructions, the irret-u and irret-s. This is to separate your return to user space and your return to kernel code. I'm told that is to make microcode faster, which is great. Also, this finally removes ring 1 and 2 from the architecture. Rings 1 and 2 have been slowly bit rotting since the 386 introduced paging. And set made them basically unusable, but still kind of there and lingering. Fred formally prevents the ability to enter ring 1 and ring 2, which is probably a good move. There's also a new load kernel GS instruction, which behaves exactly like the existing mov to GS, but updates the shadow base, not the active base. So that is exactly what we want when we are context switching applications. So that's a lightning fast overview of Intel and AMD's stack switching. Here are various links. The top one is actually a proper prose write-up I did of this, which led to some of the public discussion. There's the AMD link in the middle, that's a PDF, and then there's the Intel link to the bottom, which is on their website. As I said, right now both of these are open for technical review, and both of these documents have information for how to submit feedback to the architects on them. And at that point, if anyone has kept up the entire way, I should probably ask for some questions.
I don't suppose there is a way to get the vendors to agree on one proposal?
The vendors have been told in no uncertain terms from a group of people that there shall be one answer to this, and that they are going to sit together and figure out what it is. How well this is happening in practice remains to be seen, but yes, there are a lot of people who care very much about there only being one solution in the long run. The reality is there are bits of both that are nice, and I can certainly sit down and say which half from Intel and which half from AMD I'd like to see. Ultimately, that will be guided by what is doable in microcode and in the processors, and in line with various processor timelines.
So I guess maybe this is just wishful thinking on my part, but if we're going to have all that, can we also have instruction pre-decoding for VTX as with ARM?
No, you can't. I have requested this from both vendors, and they have both said no. The problem is that by the time you get to take a VM exit, you only have the micro-op that you were working on. The architectural instruction stream has long since been removed from the pipeline. AMD do have a way of getting this back, but it's racy and it doesn't work correctly, and you cannot actually use it for security purposes.
Is the micro-op enough to tell the hypervisor what it needs to do?
No, because a lot of the interesting things are many micro-ops. Sorry, I'm just looking through the conversation. Right, to Edvin's question about SMIs, yes, SMIs are a thing. By and large, they happen entirely behind our back. There's nothing you can do about them. There are some implementation challenges. So, for example, the MOV-SS block does actually block SMIs by one instruction, but that is a microarchitectural detail, not an architectural one. Basically, there's nothing you can do. SMIs will happen, and they will happen behind your back. Yes, it is perfectly easy to have an NMI nested inside an SMI. By default, entry to SMM mode will block NMIs, but the SMM handler can re-enable NMIs if it wants to handle them, and some do. Okay, to Demi's question about SKInit, yes, AMD already give you that. That exists, has existed for 15 years now. So AMD in particular have the global interrupt flag, which is set, which you use around VM run and also immediately out of SKInit, and it blocks absolutely everything. It blocks NMIs, it blocks SMIs. Don't go writing a hypervisor that never clears the global interrupt flag, because then your OEM firmware will get sad. Right, I think we're coming up on time, and it would be rude to encroach onto the next topic. So, thank you all very much. Hopefully, this made a little bit of sense to some people. Obviously, if you have further questions, I'm generally around and can probably answer them in more detail. There was quite a lot of things that I had to breeze over because, frankly, half an hour is not very long to do this in. Thank you.